The topic of this section is improper integral. Improper integral is a generalization of what we were talking about often, namely the definite integral. Let me repeat what we mean by the definite integral to stress the differences, the details that we will generalize, that we will relax. If a function f is continuous in a closed interval, and now this is important, in a closed interval, AB, assuming AB two real numbers such that B is not less than A. These square brackets in the English literature mean the closed interval, that means interval including the endpoints. In the Czech literature, they use angle brackets for the closed interval. So if a function is continuous in a closed interval, then the antiderivative exists. Sometimes we can find it, sometimes not, but it exists. And by definition, the definite integral of this function is the antiderivative, capital F, evaluated at b and a and subtracted. If the function is continuous in the closed interval, then the antiderivative is also continuous in the closed interval. So these two numbers exist, and the difference is no problem, the difference of two real numbers. Well, I would like to stress the information that the function is continuous in a closed interval. This is a strict condition. It has many results, many implications. If the function is continuous in the closed interval, then the function is bounded from above, bounded from below, so it is bounded, and it attains its maximum in this interval, and it attains its minimum in this interval. These are quite strong properties, useful properties of the function. Well, and the generalization is, if we relax the interval from being closed, and we will be happy with open interval. So, it is not clear that small f at a exists. It is not clear whether small f at b exists. And what is even worse, that fb exists and fa exists. But then, if we are not sure whether these values exist, we have some machinery how to replace this information, namely limit. So instead of this, we consider limit of the antiderivative for x approaching b, and we don't know what happens after b, so we can approach b only from the left. And instead of fa, we must consider the limit of capital F of x for x approaching a. And because it is not clear what happens to the left of A, we must approach A from the right. And this is the definition of the improper integral from A to B. So this is the definition of the improper integral from A to B of a function f, where capital F is the antiderivative, and this works, or this must be considered when the function is defined or continuous in the open interval only. What does it mean? What is new in this concept? What functions, how a function may look like if it is continuous in the open interval only. It may go to infinity, or it may behave in a very wild way. Consider a function that is continuous in the closed interval. So some function here, some function value here, and some behavior like that. No problem. And when the function is continuous in the open interval only, then it may happen that when you approach b, it goes to infinity. Or the function may go to minus infinity. Or the function, when x approaches b from the left, the function may oscillate in a very wild way with no limit. And similar behavior when approaching a. It may go to plus infinity, minus infinity, or it may oscillate without any limit. So this is one way why we want to generalize the definite integral to the improper integral by replacing the antiderivative values by limits. And another good reason to consider the improper integral is when a or b or both are not real numbers. We may consider a to be minus infinity, and we may consider b to be plus infinity. So here, for the definite integral, a and b must be real numbers. But for the improper integral, a and b may be plus or minus infinity. Let me give you one example of an improper integral where everything is almost fine. Consider the function e to the power of x and say we want to find the area of this region. The area, well, we start with some fixed a and b is 0. So we can consider the integral from a to 0 of into x dx, and then we push a further and further to the left. Scientifically speaking, we consider the limit for a approaching minus infinity. So this will be limit for a approaching minus infinity, and antiderivative of e to x is e to x from a to 0. E to 0 is 1 minus e to a. And now when a approaches minus infinity, then this expression goes to 0 and the result is 1. This is quite an important result. We have a region. Let me sketch it once again. We have a plane region that is not bounded. It does not fit in a finite sized circle. It is not bounded. It stretches to infinity. But even though the region is not bounded, the area is bounded as a number. This is quite an important point, not trivial. We can have a plane region that is not bounded, it stretches to infinity in one direction, but the tail is so thin that the area is still finite, equal to 1. Nice number. Another example of an improper integral, which is a number. Well, the terminology. If these two limits, both of them exist and are finite, are proper, then we say the improper integral converges. And if they don't exist, or if they are not finite, then we say the integral diverges. Consider the function 1 over x squared and consider the area of this region. Well, back to the previous case. this is the full notation. Integral from a and limit for a approaching minus infinity. So this is the full notation, this is the correct way how to write it. But we often use a simplified, a short notation. We write integral from minus infinity to 0. Integral from minus infinity to 0. Some call it abuse of notation. But this is very frequently used, and this means limit of a approaching to a limit of the integral from a and the limit for a approaching minus infinity. So this is the shorthand, this is the abbreviation, and this is what it means. Similarly, for 1 over x squared, we could write integral from 1 to infinity, which means integral to some fixed b, the upper limit, and we consider the limit of b going to infinity. The antiderivative is minus 1 over x from 1 to infinity. And again, this infinity means there should be b and the limit for b approaching infinity. But 1 over infinity is 0, minus 1 over 1 is 1. So once again, this region, although it is not bounded, it stretches to infinity on the right, but again, the tail is so thin that the area is finite. The area is bounded. So we say that this integral converges, this integral converges. But not all improper integrals must converge. Consider a similar case, the function 1 over x. So the area from 1 to infinity, 1 over x dx. The antiderivative is logarithm. But logarithm of infinity is infinity. So, although this region is quite similar to the previous case, then now the tail, even though the integrated function does go to 0 for x approaching infinity, you see, this graph does have its asymptote, the x-axis, but still it goes to 0 so slowly that the area is infinite. Well, once again, this is an abbreviation for the full notation. A is limit for b approaching infinity, 1 to b. So the full notation will be, once again, limit for b approaching infinity, and the antiderivative is logarithm from 1 to b. So if we write it very, very slowly, limit for b approaching infinity, logarithm of b minus logarithm of 1, which is 0. And now logarithm of b for b approaching infinity is infinity. So this integral diverges.